Good day everyone. This entire video is a compilation of short videos from the internet that will help us learn about nitrogen and sulfur pollution. In particular, we will be watching 4 videos. First is on nitrogen pollution, next is on photochemical smog, third is about acid rain, and lastly, about flue gas desulfurization. You can read on this in Learning Guides 2.9 and 2.10, but most of the lessons there are already covered in this video compilation. So let's jump right in and watch the videos.
Nitrogen is abundant. 78% of the air consists of nitrogen in the form of N2. This form of nitrogen is very stable, or in other words, not reactive. In addition, nitrogen is an essential element of all living beings. But before it is used by them, it has to be converted into reactive forms, such as ammonia or urea. This can be done by specialized microorganisms or in large chemical factories. Since 1890, the yearly anthropogenic production of reactive nitrogen has increased 9-fold. If too much reactive nitrogen is released into the environment, it can have many negative effects. Let's see how human excreta contributes to the harmful release of reactive nitrogen into the environment. Reactive nitrogen compounds, such as urea, ammonia or nitrate, are major components of fertilizers. They are applied to the soil to increase agricultural production. Plants need nitrogen to grow, and most plants take up reactive nitrogen from the soil. Humans also need nitrogen and receive it from the food they eat. A large amount of the nitrogen we take up as food is excreted in urine together with most of the other nutrients. In fresh urine, nitrogen is present as urea. When the urine is exposed to the environment, urea is spontaneously converted by bacteria into ammonia. When large amounts of urine or wastewater reach open bodies of water, the high concentration of ammonia is toxic to fish. Also, nitrogen-containing compounds produced from ammonia can lead to massive algae blooms that can cause the destruction of aquatic ecosystems and fish stocks. If large amounts of reactive nitrogen get into groundwater, the nitrogen can be converted to nitrite and nitrate. High concentrations of both compounds are harmful to humans. Urine can also pollute the air. When urine is not properly handled and stored, it releases ammonia into the atmosphere. The degassing of ammonia can have multiple negative effects on human health and the environment. Ammonia in the atmosphere is converted into aerosols, which can travel deeply into lung tissue and cause damage. The formation of aerosols is compounded by urban emissions, such as air pollution from industry and vehicular traffic. The smell of ammonia gas is extremely unpleasant. However, this smell helps to keep us from getting poisoned by the toxic gas. Nevertheless, chronic inhalation of small concentrations can attack mucosae, eyes, and the lungs, and lead to respiratory illnesses. To sum up, reactive nitrogen is valuable and important for plants and humans. That's the reason why so much is produced in chemical factories for synthetic fertilizer. Yet, if it is excreted and released in abundance into the environment, it becomes a health and environmental problem. When urine is properly stabilized, it maintains its valuable nutrients, limiting the hazardous release of nitrogen into the environment. As nitrogen from stabilized urine does not degasify, producing fertilizer from it is not harmful to humans or the environment, and it also does not have malodor. If reasonably applied, the nitrogen can be brought back to sustain human nutrition. By closing the nutrient loop, energy-intensive fertilizer production and transport can be reduced. If the production of industrial nitrogen is decreased by recovering nutrients from urine, the discharge of nitrogen into groundwater, open water, and the atmosphere is also reduced. And this decreases the potential of future environmental and human health hazards caused by the overaccumulation of nitrogen in the environment. Recovering nutrients from urine to be used as fertilizer to support nutrition is a sustainable and environmentally friendly way to use these nutrients and limits the destructive effects of nitrogen.
First, we have to know what is smog. Smog is a mixture of fog and smoke which occurs in some busy industrial cities. Smog is of two types. One is classical smog and another is photochemical smog. Classical smog is produced by the combustion or burning of fossil fuels like coal, petrol, or gasoline, and caused by a mixture of smoke and sulfur dioxide present in air. Classical smog is also known as London smog. It is reducing in nature. It occurs in cool, humid climate. The major constituents are smoke, fog, and sulfur dioxide. It can occur both during the day and at night. In December 1952, London was trapped in a deadly cloud of fog and pollution for 5 days. At the time, the city ran on cheap coal for everything from generating power to heating homes, which was the result of classical smog. Photochemical smog is a type of smog produced when ultraviolet light from the sun reacts with nitrogen oxides and volatile organic compounds in the atmosphere. It is also referred to as summer smog or Los Angeles smog. It is an oxidizing smog and visible as a brown haze. It only happens in the presence of sunlight. Major constituents are hydrocarbons, ozone, PAN, and NOx. It is most prominent during the morning and afternoon. Photochemical smog formation is influenced by the weather conditions such as warm, sunny days, gentle winds, lower level inversion, which is also known as thermal inversion, combustion of hydrocarbon and nitrogen oxides. Sources of photochemical smog pollutants: volcanic eruption, forest fire, automobiles, industry, and power plants. Reaction of photochemical smog. Nitrogen and oxygen combine in the combustion process to form nitric oxide. This nitric oxide oxidized in the atmosphere to produce nitrogen dioxide. Sunlight breaks down nitrogen dioxide into nitric oxide and an oxygen radical. The oxygen radical combines with molecular oxygen to form ozone. Ozone is the main component of photochemical smog. Nitric oxide can remove ozone by reacting with it to form nitrogen dioxide and oxygen. Alternative reactions: nitric oxide and nitrogen dioxide can also react with the hydrocarbons instead of ozone to form other volatile compounds known as PAN or peroxyacetyl nitrate. Reactive hydrocarbon, those with C double bond C from the auto exhaust, interact with ozone to form a hydrocarbon-free radical. The radical rapidly reacts with oxygen to form another free radical. This reacts with nitric oxide to produce nitrogen dioxide and another free radical. This new free radical next interacts with oxygen to yield a stable aldehyde and hydroperoxyl radical. The hydroperoxyl radical then reacts with another molecule of nitric oxide to give nitrogen dioxide and the hydroxy radical. The hydroxy radical is extremely reactive and rapidly reacts with a stable hydrocarbon to yield water and regenerate the hydrocarbon-free radical, thereby completing the cycle. The aldehyde may initiate another route by interaction with the hydroxy radical, leading to the formation of an acetyl radical, peroxyacyl radical, and finally peroxyacetyl nitrate, PAN. Peroxyacetyl nitrate is also known as peroxyacyl nitrate. Effects of photochemical smog. Photochemical smog's effects cause eye irritation, damage to the respiratory system, and vegetation. Photochemical smog was first identified in Los Angeles in 1944. In 2017, photochemical smog enveloped large parts of Beijing. Also, in November 2017, the air pollution spiked far beyond acceptable levels in Delhi.
In this video, you will learn that in two quite different ways, the burning of fossil fuels can cause our rain to become acidified. Sulfuric acid arises from the burning of coal and oil, mainly in power stations, whereas nitric acid arises from the exhaust pipes of our motor vehicles. You will also see some of the effects acid rain has on our environment. Firstly, it's important to understand that rain is naturally slightly acidic. Whilst falling to the ground, the rain dissolves carbon dioxide from the atmosphere to form carbonic acid, a weak acid giving natural rain a pH of 6. It's when we burn fossil fuels that much stronger acids get into our rain, to form acid rain with a pH as low as 3. When the pH changes from 6 to 3, what do you think the acidity increases by? 2 times? 3 times? 10 times? 1,000 times? Pause and think. Remember that each change of 1 in pH is a 10-fold change in acidity, so changing from 6 to 3 is 10 times 10 times 10, or 1,000 times more acidic. We'll consider sulfuric acid first. Plants need a little sulfur to grow. They obtain it from sulfates, for example potassium sulfate, found naturally in the soil. The sulfates are taken up by the plant's roots, and sulfur atoms become bonded to carbon atoms in the leaves' proteins. When plants die and eventually form coal and oil over millions of years, these sulfur atoms remain bonded to the carbon atoms. The sulfur content of coal and oil is usually between 1 and 4% by weight. What do you think is produced when fossil fuels containing sulfur are burnt? Pause the video whilst you think. When the coal is burnt, the sulfur and the carbon atoms join with oxygen from the air and are released into the atmosphere as carbon dioxide and sulfur dioxide. In the presence of sunlight, a photochemical reaction will take place where sulfur dioxide reacts with more oxygen to form sulfur trioxide. This dissolves in the rainwater, forming sulfuric acid. Let's now consider how nitric acid gets into the rain. In the high temperature conditions in the cylinders of our motor vehicles, a small amount of nitrogen and oxygen from the air can react. Remember that air taken in to combust the fuel is nearly 80% nitrogen. So exhaust gases from vehicles contain small but significant amounts of nitrogen oxides. Once the oxides of nitrogen are in the air, they react with more oxygen, just like we saw with sulfur dioxide, and dissolve in the rainwater to form nitric acid. If the rain falls on limestone soils which are alkaline, the acidity may be neutralized. However, if the rain lands on neutral or acid soils or on vegetation, then it can cause damage. So why is this acidity harmful to living things? Well, living things don't grow well in acid conditions, and it's easy to demonstrate this. Soak a slice of bread in vinegar and another in pure water, leave them open for a little while, and then leave them covered for a week. You will find that the bread soaked in vinegar has not gone mouldy, whereas the other bread has. In fact, we use vinegar to preserve food in a process called pickling. This is the case because certain enzymes which are vital for growth are unable to function in acid conditions. The other main problem is in the soil. Whilst naturally occurring toxic metals such as aluminium are insoluble and therefore fairly harmless in neutral soil, they become soluble in acidic soil. They then get taken up by living things and take the place of essential metals such as zinc and iron. To add to this, the hydrogen ions in the acid rain will replace essential metal ions such as potassium, magnesium and calcium, which are normally held in the clay soil, causing these essential metals to be washed deep into the subsoil away from the roots of plants. So to summarize, normal rain is slightly acidic due to the dissolved carbon dioxide, but acid rain contains sulfuric and nitric acid, making the rain 1,000 times more acidic and dangerous for many living things. Sulfuric acid arises from the burning of fossil fuels containing sulfur. Nitric acid arises from the combustion of atmospheric oxygen and nitrogen in the high temperature conditions in the cylinders of petrol and diesel engines.
In some instances, sulfur dioxide from combustion is removed from the flue gases by using it either to produce sulfuric acid or gypsum for construction. These products can then be sold to help offset the cost of running the flue gas desulfurization plant. In both cases, oxygen is used to help encourage the necessary reactions that need to take place. In the case of sulfuric acid, adding excess air to the sulfur dioxide and vanadium oxide converts it to sulfur trioxide, SO3. When combined with water, this produces H2SO4, or sulfuric acid. In the case of gypsum, limestone slurry used in wet scrubbing processes combines with sulfur dioxide to produce calcium sulfite. When subjected to a forced oxidation process involving the addition of water and oxygen, the sulfite is converted into gypsum. In addition to these processes, oxygen is also required in flue gas desulfurization processes using seawater. As the seawater absorbs the sulfur dioxide, oxygen is added, creating a mix of sulfate ions and hydrogen, which in turn converts to water and CO2 gas. In all three cases, using an oxygen probe to accurately measure oxygen concentrations can help to regulate the conversion of sulfur dioxide. For more information about ABB's AZ Analyzer range, contact your local sales representative or visit www.abb.com/measurement.